Chapter number 3, using the application tracing tools. After you have completed this lesson, you should be able to discuss the steps that should be performed before tracing, describe application tracing tools, and use the SQL tracing as well as the end-to-end application tracing facility. You should also have learned how to use the trace session utility to consolidate SQL trace files, and also how to use the tkprof utility to format those trace files. At the end of this chapter, we're also going to see how you have to interpret the output of the tkprof command. The first topic of this chapter is going to give us an overview of application tracing. Now you're going to enable application tracing whenever you want to tune SQL statements. And you're going to disable it afterwards when you're finished, because running application tracing increases system overhead. Oracle recommends that you use the DBMS session or DBMS monitor packages to enable and disable SQL tracing for a session, for an instance, or for a service. Now, before you start tracing, make sure that you're going to determine the right trace file location and also choose the most impacted sessions or instances or services for which tracing should be enabled. Then you're going to enable tracing and you're going to let the users generate their workload as they always do. Once the workload has been generated, disable the tracing, because I've already mentioned that tracing will increase system overhead. Now, whenever you're going to perform tracing, this is going to generate trace files, and via the utility trace session, you can consolidate trace files into one consolidated trace file. And then you're going to use tkprof in order to format the contents of that trace file and place the output into a readable output file. Once you have done this, you have to take your time to interpret the tkprof output. So before you start tracing, determine the location where those diagnostic trace files will be placed. In an Oracle database, that location is the automatic diagnostic repository. The automatic diagnostic repository, the ADR, is a file-based repository for database diagnostic data, such as those trace files. The trace location is set via the diagnostic dest initialization parameter. Also, choose the most important affected clients, services, module, actions, users, or sessions that require tracing. So maybe find those sessions that have the high CPU consumption, or those sessions that experience the highest amount of waits of a certain type. Or maybe find out those sessions that spend the most time inside the database. Yeah, for example, it may be the users who are experiencing the problem the most severely, or users who are aggressively accumulating time inside the database. Now, which application tracing tools do you have at your disposal to perform the SQL tracing or the end-to-end application tracing? Well, you can enable application tracing by using one of the following procedures of certain packages within your Oracle database. So you have the possibility to use the package DBMS monitor as well as the package DBMS session. Via DBMS monitor, you can enable tracing at the database level or enable it at the session level. You can enable it at the client ID level. You can even perform the tracing at service level. For that, you have the appropriate procedures. You can also use the package DBMS session in order to enable tracing for your own session. Or you can also do this via the DDL command, alter session set SQL trace. But Oracle recommends that you're using the packages DBMS monitor and DBMS session to enable SQL tracing or end-to-end application tracing. So how can you use the SQL trace facility. And when are you going to use this SQL trace facility? Well, you're going to use the SQL tracing facility if you want to retrieve traces from specific impacted sessions or from specific users, or you want to retrieve traces from an entire database. Now, tracing a specific client is usually not a problem in the dedicated server model, because in a dedicated server model, a single dedicated process serves a session during its lifetime. All the trace file information for that session can be seen from the trace file belonging to the dedicated server serving it. So if you are working in a dedicated server model and you have this client OE that makes a connection to the instance, it will get its own server process, its own dedicated server process. Whenever that client is going to launch a workload, it's going to launch specific SQL statements, those SQL statements are going to be executed by the dedicated server process for that client. You then have the possibility to say, look, I want to trace that specific client OE. Well, everything that its dedicated server process does for that client OE can then be traced, and that information will be placed inside a trace file. So, for instance, how can you trace your own session? Well, let me show it to you via a small demo. Well, look, I have here an environment, and what do I see is that I'm calling the utility SQL Plus, and I'm logging in as user HR into the pluggable database ORCL PDB. Now, what I'm doing is, before I'm enabling the tracing, I'm going to set the trace file identifier for this session. I'm setting it to HR session 1. Later on, when I have to locate that trace file, this will make my life easier, because that trace file identifier will be a substring for the trace file name being generated. So it's much easier for me to locate the exact trace file. And then what you're going to do, you're going to use the procedure session trace enable of the package DBMS monitor in order to enable the SQL tracing for your own session. And then you're going to run your workload. So as you see here, that I'm executing this query where I'm obtaining the last name of the employee who has employee ID 100, plus I'm also going to perform this select statement that retrieves all columns and all rows from my table dpar. Now, once the workload has finished, you have the possibility to disable the session tracing by executing the procedure session trace disable of the package DBMS monitor. Or what you can do is, you can also simply quit the session. This will disable the tracing as well. Well, I have now traced my own session. Tracing information is now being stored in my trace file. Where can we find that trace file? Well, you will find it by default in the automatic diagnostic repository. But what is the location of that diagnostic repository? Well, look up the value specified in the parameter diagnostic dest, and in my case it points to the directory U01 app Oracle. It's underneath subdirectories of this directory that my trace file will be placed. So I've quit my session, which disables the tracing. And then what I did is I changed the directory to U01 app Oracle. Now, underneath that diagnostic repository, Oracle will automatically create some subdirectories. You will always find the directory DIG of diagnostics. Because we talk about a database, you will have a directory RDBMS. The name of my database is ORCL, which is being accessed via instance ORCL. So this is a streamlined directory structure. And underneath this directory, it creates the trace directory, and that is the location where the trace files will be placed. And look, what I'm doing is I'm asking a listing of all the files underneath this trace directory, but I only want to see those trace files that have the substring HR session within their name. And what do I see is that there is indeed a trace file being generated holding the substring HR session 1, which is the trace file identifier that I've set before I started the tracing. Now, it's in this trace file that the executed workload between enabling and disabling the tracing for my session is being placed. Now look, I'm going to open this specific file. Now what you will see is, this is the content of that trace file. It's in Oracle's own format, but I can search for the keyword employees. And you see here, select last name from employees where employee ID equals 100. And I can also search for departments. And here you can see the select stuff from departments that I did in my session while I was tracing my session. And information has been captured and placed inside this trace file. Another example of tracing a specific user is that you have the possibility to create a trigger where you can say, look, this trigger will be fired whenever a login happens upon my database, where the user is like, and you specify when you create that trigger the name of the user that you would like to trace. So I can state, create me a trigger that fires whenever somebody logs into a database, like for instance user Christoph with my name, for instance. This trigger will fire, and then what's happening is the procedure session trace enable is being called of the package dbms monitoring to activate the SQL tracing. Plus you have the possibility, if you also want to capture weight information into the trace file and or bind variable information inside that trace file. If then that person logs out, I've told you when you log out the tracing is being disabled, well then locate and review that trace file. Now, we have discussed how you can perform tracing within a dedicated server model. It's quite simple. You only have to trace the dedicated server process for a specific session. However, sometimes you need to perform tracing within a shared server model. And that is usually a problem because a client is occasionally serviced by different processes. This makes it difficult to get a complete picture of the life cycle of that session. So what you're having is, you can have a client C4 that logs in a multi-tier environment. It will not get its own dedicated server, but whenever it launches its first request, it can be that that request is being handled by this shared server process. It can be that whenever client C4 is going to launch a second SQL statement, that SQL statement is now being executed by this shared server process. Now, if you're going to perform tracing, you're going to trace what are the server processes doing inside my database environment. Yeah, but now you have the problem that all of those shared server processes that will carry out requests made by the clients that have connected to the multi-tier environment. So that is now a challenge to perform tracing if I only want to trace what client C4 is doing within my database. Yeah, what I will need to do is, I could say then trace all three shared server processes, but those shared server processes will also perform workloads generated by other clients. That's one thing. Plus also each server process will generate its own particular trace file, which you can, and we'll see that later on, which you can then via the trace session utility consolidate into one big trace file. This is being covered later on in this lesson. Now, in order to perform this tracing in a shared server model or in a multi-tier environment, you can make use of end-to-end application tracing. Now, end-to-end application tracing simplifies the diagnostics of performance problems in a multi-tier environment. So in a multi-tier environment, a request from an end client is routed to different database sessions by the middle tier, making it difficult to track a specific client. Now, via a client identifier, you can generate a unique trace for a specific end client through all the tiers to the database server. Now, if you talk about end-to-end application tracing, you have to talk about services. And if you talk about services, you can then also talk about modules and actions. And this end-to-end application tracing is something that you can enable and then afterwards disable at the service level or at the service module or at the service module action level. And any settings that you're going to set for this end-to-end application tracing will persist across instance restarts. Now, the first thing that you need to do is to perform this end-to-end application tracing is to set up services. Now, what is a service? It's something that has already been around for quite some time, but a service is actually nothing more, nothing less than a logical representation of my database environment to the outside world. That's one thing, and it's also something completely dynamic. Now, let me show you this. Please look. I have here another example. So you see here that I logged into my pluggable database URCL PDB. Well, what you can do is you can present this URCL PDB, this database. It's a pluggable database, but this database, you can present it to the outside world as a specific service. And how are you going to do this? Well, you logged into the pluggable database URCL PDB, and you're going to use the package dbms service. You call the procedure create service to say, look, I would like to create a service with the name service1. This is completely up to you, what service name that you would like to use, but I would like to show the pluggable database URCL PDB to the outside world as service number 1. And then you're going to start that particular service via the procedure start service of the package dbms service. Now, once you have started up the service, by default, the listener on port number 1521 will be made aware, look, there is a service number 1 being created that is shown as a service of storing data to the outside world. And you will see I created and started my service. And what do I see is that my listener is now aware, look, there is a service number 1, which represents instance URCL, but I've created for pluggable database URCL PDB. But it's simply a logical name that I have been given to my database environment. And then what you're going to do is, if you then want to perform tracing for a specific application in a multi-tier environment, you can then say, look, any connections that are being made by that specific application have to be made via service number 1. Any other application that is connecting upon the same database environment is not going to establish services to the database seen as service 1, only that one particular application. And then I have the possibility to trace what's happening inside my database, but seen as service 1. And if I have my one application, which is the only application connecting to my database as service 1, I'm going to be able to trace what that particular application is doing within my database. Now look, what did I do is I have, and that's what I'm trying to explain on slide number 17. I have here my TNS names.aura. Going to open this. And what did I do is, in my TNS names.aura, I created a connect descriptor called TNS_service1. And if I'm going to use that connect descriptor, I'm asking to contact the listener on port number 1521 and ask to establish a connection upon my database environment as service number 1. So this is my connect descriptor TNS service 1. Now let me show you something. Now I'm going to log in as user HR and I'm using TNS service 1. I'm connected to pluggable database ORCL PDB, but logically seen as service 1. And look what a DBer can do. DBer can now, via $session, find out what are the current sessions upon my database environment. But you see that I'm only interested in those sessions where username is HR. I'm going to run this select statement. And what do I see is that I have indeed a user, HR, which has a session uniquely identified by that specific SID and serial number combination, but it is a session upon my database environment, but connected, logically seen as service number 1. And just to show you this, look, I'm going to run here SQL plus HR, but I'm going to use the connect descriptor ORCL PDB, which connects upon the same pluggable database, but not seen as service 1, but seen as another logical name for the same pluggable database, ORCL PDB. And look, if now I go back to this session, I'm going to run this query. I see now that I have 2 sessions upon my database environment as user HR, but one session is connected to the database seen as service 1, while another session is connected to the same database environment, but seen as service ORCL PDB. And now what I can do is, and we will see that later on in the slides, I can now state, look, I would like to trace all the SQLs that are being executed in my database environment, but seen as service number 1. So in a nutshell, a service is nothing more, nothing less than a logical representation of my database to the outside world. Let then your application connect upon that specific service, and then you have the possibility via the procedure service module act trace enable to indicate that you only want to trace those SQLs executed in the database environment but seen as that specific service. Now, once you have set up services, you can also then within a service perform module tracing. Now, what is the following? Well, this example shows how you can set for this particular insert statement, how you can give it a module and action name. So you can say, look, I have a procedure with lots of coding in it, but I'm only interested in tracing this insert statement of that procedure. Well, I'm going to call upon the package dbms application info set module, and I'm putting up flags. I say, look, the module name is add employees. The action name is insert into emp. It's actually reflecting only this particular insert statement. And after that insert statement, I'm going to onset the module and action name. I'm going to onset the flags. Now, what I cannot do is, let's say, for instance, that I'm logging into my database, but as a specific service, and then I'm going to execute this procedure add employees. But the DBer says, please trace everything that's happening inside that particular service where the module has been set as add employees. And what you will get is that tracing will be done, but only the tracing information will be collected for that particular insert statement. So this gives you the possibility, this tracing by service, module and action. It enables you to focus your tuning efforts on specific SQL rather than sifting through a trace file with SQLs from different programs. Only the SQL statement, in this case the insert statement, that are identified within this module and action are recorded in the trace file. Now, this is another example where you can perform action tracing. So you can call or add the following procedure in your code to set the name of the current action. So you can say, I have here 2 updates and a commit, and that's the only thing that I'm interested in tracing. Well, I'm going to use the package dbms application info, and I'll say I'm setting the action name to, it's a simple flag, transfer from check to savings. After my 2 updates and the commit, I'm onsetting that flag. Well, now, if I'm going to connect to my database as a specific service, and I'm going to execute this procedure, balance transaction, it will only capture tracing information for the 2 updates and this particular commit. I'm not interested in any other SQLs being executed for that service. No, only those SQLs executed against that service that have been flagged, in this case with action name transfer from check to savings. What you can also do is via this dbms monitor is that you have the possibility to trace via the client ID. So whenever somebody logs in, it can then, for instance, launch the procedure set or a session ID, and the person executing this procedure gives in, for instance, the value C4. Well, if that person does that, if then the DBR says, I would like to enable tracing for those sessions where the client ID has been set to C4. If then, after I've enabled it, another session logs in, carries out the procedure set or a session ID, and also gives in client ID C4, automatically that session will then be traced. And I can even indicate if I'm interested in also capturing tracing information concerning weights and or bind variables. Now, on one of the previous slides, we talked about session tracing, and we recommended to use the package dbms monitor. Now, you have the possibility to trace all the sessions in the database. We'll simply call the procedure database trace enable of that package dbms monitor. Now, I've shown you an example on how you can trace your own session, but the DBR also has the possibility to trace sessions from a distance. For instance, if I go back to my demo environment, if I only want to trace this specific session, I only have to look up this SID and that serial number. And then I can, via the procedure session trace enable, I can then provide the session ID as well as the serial number of the session that I would like to trace. So DBR has the possibility to enable tracing from a distance. Now, Oracle recommends to enable tracing for a session to use dbms monitor. However, dbms monitor constructs can only be invoked by users that have the DBA role. Now, if I have a normal user logging in and that user wants to enable SQL tracing for his or her own session, and I don't want to give that person the DBA privileges, well, those persons can make use of the package dbms session, calling the procedure session trace enable to enable session level SQL tracing for his or her own session. Also, I've already shown you that in my demo. Via the ultra session command, you can set up a trace file identifier to easily locate the trace file for that specific session that has set that specific trace file identifier. Now the next topic in this chapter is talking about the trace session utility. So we're going to see what is the trace session utility, what can you do with this, and how you invoke that trace session utility. The trace session utility consolidates trace output from selected trace files on the basis of several criteria, such as session ID, client ID, service name, action, and module name. After the trace session utility has merged the trace information into a single output file, the output file can be processed by tkprof. In order to use the trace session utility, you're going to call the executable trace session, which you're going to provide several parameter values. You have the output parameter, where you specify the file where the consolidated trace file should be generated. You can then also specify which trace files of which session ID should be consolidated, or which trace files generated by which client IDs should be consolidated. Same story for trace files that have been generated against a service name, an action name, or a module name. You can even specify the list of trace file names separated by spaces in which the trace session utility should look for trace information. Now I have prepared a small example where you can see the utilization of the trace session utility. Let me take my demo environment. And what do I see here is that I have created a session as user HR, but that session connected to the instance as service 1. I also have another session of HR that connects also to the instance as service 1. And I have a third session of HR that connects to the instance but as service ORCL PDB. Now one session of HR connected to service 1 executed this particular select statement, while the other session of HR also connected to service 1 carried out this select statement looking for the employee with employee ID 101, while the session of HR that is connected to the ORCL PDB service is going to execute select star from department. Now before I executed that particular workload, what did I do is I could find out which are the sessions where username is HR, and I can see that I have 3 sessions, 2 of them connected to the instance as service 1, and then I have enabled the tracing of the SQLs executed in the database but seen as service 1. And that means that it will only have traced the select statement executed by that session as well as the select statement executed by that session. This session that is connected to the instance as service ORCL PDB will not be traced because I was only tracing service 1. So the select star from departments will never be traced. Now I had 2 sessions of HR that were connected to the instance as service 1. Well, this will generate 2 trace files. And those 2 trace files will be located default underneath the trace file directory that is based upon the directory value of the parameter diagnostic test. Now in my case, the default trace file directory is U01 app Oracle, which is the value of diagnostic test, and underneath that directory I have the automatically created directories DIG, RDBMS, ORCL, the name of the database, ORCL, the name of the instance, and there I have the directory trace where by default those SQL trace files are being placed. Now what I'm doing is, via the trace session utility, I'm asking, can you please create me a consolidated trace file called service1_trace, but only consolidate those trace files that have been generated against service 1. This results in a new trace file, but the content of that trace file is still in Oracle's proprietary format. So if I'm going to open that trace file, you still see it's not in a formatted format, in fact. But if I look up employees, for instance, I'm seeing here select staff from employees where employee ID is 101. That was a statement executed by this session that was connected to service 1. And I can search now for the next occurrence. And you see here select staff from employees where employee ID is 100. And that's the tracing information of the SQL statement that was executed by this session that was connected to service 1. If I would search inside that trace file for departments, you see that he doesn't find a pattern because that was select staff from departments executed by a session that was connected to the instance, but not as service 1 at the moment that I did this tracing. Now, in the book, you have another example of the trace session utility where you have 2 sessions, and both sessions are going to put their client identifier to HR session. And then in the 3rd session, I'm going to enable tracing for those sessions where the client ID has been set to HR session. And I'm not interested in capturing wait information and bind information. Then the 1st and the 2nd session perform their workload. Once this is finished, I can then via the procedure client ID trace disable the tracing of sessions that have their client ID set to HR session. Now, because I had 2 sessions where the identifier was set to HR session, I will have 2 trace files. Well, via the trace session utility, I can ask, can you have a look underneath this directory, look at the trace files, and consolidate the trace files that have been generated against sessions where the client ID is set to HR session, and please consolidate them into one trace file called mytrace.trc. Now, a trace file, or the consolidated trace file generated by the trace session utility, shows the trace information in Oracle's proprietary format. Now, you're going to use the tkprof utility to produce a more human readable format so that we can interpret much easier the captured tracing information. Now, the tkprof utility parses SQL trace files to produce more readable output. Remember that all the information in tkprof is available from the raw trace file. So tkprof is not going to overwrite a trace file. No, he's going to read a trace file. He will format that trace file, and the output will be stored in a separate report file. The resultant file contains the most consuming SQL statements at the start of the file. Now, if you're going to use the tkprof utility, there are several options that can be specified. Now, if you want to use the tkprof utility, you're going to call upon the tkprof executable, where you will have to specify which raw trace file to read and where the formatted output should be written to. That is then your so-called output file. But then you can specify several parameters, like you have the weights parameter. And with that parameter, you can specify whether to record the summary for any weight events found in the trace file. Values can be set to yes or no. Also, you have the possibility to sort the traced SQL statements in descending order of the specified sort option before you list them in the output file. Which option that you can use to perform the specific sorting is going to be shown in the next slides. Now, if you ask to sort the traced SQL statements in descending order, you can then specify via the print parameter to only list the first integer sorted SQL statements from the output file. If you don't set this, tkprof will list all the traced SQL statements. By the aggregate parameter, you can specify whether or not tkprof does an aggregation of multiple users of the same SQL text. With the insert parameter, you can ask tkprof to create an SQL script to store the trace file statistics inside the database. With the parameter sys, setting it to no, you can specify that in the formatted trace file, you do not want to obtain any information about the recursive calls. These are internal select statements like querying your data dictionary that are going to be executed automatically whenever information has to be looked up inside that data dictionary. With the parameters table and explain, you can ask tkprof to execute every captured SQL statement with the explain plan command to generate the execution plan, and ask to store those execution plans in the table that is specified by the table parameter. By the record parameter, you can ask tkprof to create a script file with the specified file names with all the non-recursive SQL statements in the trace file. Plus, you can specify the width parameter, which is an integer that controls the output line width of some tkprof output, such as the explain plan. Now, I have here an example prepared using tkprof, and that's the following. So, with my trace session utility, I have created a consolidated trace file. But then what did I do is, via the tkprof utility, I asked to take a look into that raw trace file and produce a human readable output and store that inside this file called formatted service1 trace.txt, and I don't want to see any of the recursive calls that have been done during the tracing of that workload. Then you can open that formatted trace file and you will see that it is shown in a much more human readable format. Now, I've told you that you can ask tkprof to sort the SQL statements captured in descending order. Now, this slide plus the next slide shows you the options that you can use for the sort parameter when invoking tkprof on how you would like to have the SQL statements being sorted in descending order. So you can ask, for instance, please sort my SQL statements in descending order based upon the number of executions that were called. Or you can say, can you please sort the SQL statements, but sorted upon the number of times fetch was being called. So you have several sort options at your disposal. Now, a tkprof report for an individual cursor includes the following structure. It contains the SQL statement, parse, execute, fetch statistics and timings. It will show library cache information, the execution plan itself, and the events weighted for by that statement. This section contains the bulk of useful information for each statement. Now, how do you interpret such a tkprof report? Well, when you look at the execution plan of an SQL statement, it's going to show you the different steps that have been carried out during the execution of that SQL statement. Now, the rows count output in this section is the actual number of rows returned at each step in the query execution, while B is the row source operation, which shows the operation executed at this step in the plan. Then the consistent reads, the reads and the writes will show you I/O statistics. So CR stands for consistent reads, D stands for the number of physical reads that should have been done, and E stands for the number of writes. These statistics can be useful in identifying steps that read or write a particularly large proportion of the overall data. And then you have the timing statistics, which shows you the cumulative elapsed time for the step and the steps that have preceded. This section is very useful when looking for the point in an access path or execution plan that takes all the time. By looking for the point where the majority of the time is taken, it's possible to narrow down several problems. Also, you're going to see parse, execution, and fetch statistics. So in this case, you see here the parse, execute, and fetch statistics of an update statement. Now, the execute phase of this update statement shows 297, and this means that this update has visited 297 blocks to find the rows to update, while current tree indicates that only 3 buffers have been accessed to then actually perform the update. And statistic J shows that only 1 row has been updated. Now, reading 297 blocks to update 1 row is a lot of work and tends to indicate that that access path is not efficient. Maybe by creating an index, this can improve the access path efficiency. Then you see here parse, execute, and fetch statistics for a select statement, for a query. Now it shows in the fetch stage that only 1 row has been returned by that query. But to obtain that 1 row, 4 blocks had to be accessed to get that particular row. Also, I'm seeing that this statement has been parsed twice, of which you have 1 miss in the library cache. So that means of those 2 parses, you had 1 hard parse, the other one was a soft parse in fact. Also, what you're seeing is that the total elapsed time is 354 seconds. Total CPU time is 230 seconds. But you see that the majority of CPU time and the majority of the elapsed time was spent on parsing. If you compare that to a total execution time in elapsed time of 17 seconds. So if people are complaining about that particular select statement, it's of no use to tune the execution plan, because you see that the execution time is far more less than the parsing time, but we need to focus on what's happening during that parse phase of that select statement to find out why it takes the majority of the time to perform that parsing, in fact. This will require some further investigation. Also, you have here parse, execute, and fetch statistics for an update statement. Now, what do I see is that this update statement has been executed roughly 490,000 times, and that in total 490,000 records have been updated. That means for every execution of this update, 1 record has been updated. Now it might be, and it's with a big certitude that you can say, that the update is part of a loop where individual values are passed and 1 row is updated per value. This is a structure that does not scale with a large number of values, meaning that it can become inefficient. One potential solution is to try to batch up the update so that multiple rows are updated within the same execution. Then sometimes the execution of an SQL statement of a user, the Oracle server must issue additional statements. Sometimes to execute an SQL statement issued by a user, the Oracle server must issue additional statements. These are called recursive calls or recursive SQL statements. For example, if you want to insert a row into a table that does not have enough space left, Oracle database makes a recursive call to allocate the space dynamically. Recursive calls are also generated when data dictionary information is not available in the data dictionary cache and must be retrieved from disk. So suppose, just to have a scenario, that the application ran in 410 seconds. When you look at the overall totals in your formatted trace file, you see that total elapsed time is 403 seconds for non-recursive statements. These are for the statements executed by the application. 0 seconds have been spent on executing recursive statements. This means 403 seconds out of 410 seconds, seen from the user's point of view, were spent inside the database. So query tuning, if people complain about the performance of the application, can indeed help in this situation. Now what you also need to verify is, was the time spent on parsing, executing and fetching? Do those phases account for the most elapsed time recorded in the trace? Now, as you can see here is that the total elapsed time of parsing, executing and fetching is indicated to be 0. This means that the total time on parsing, execution and fetching took less than 100 of a second. But it can be, although it only took 100 of a second to perform the parse, execute and fetching, that a person complains, why does it take that long to get my data back? Now I see it's not the parsing, it's not the execution or the fetching stage, because this is less than 100 of a second in fact. But if I take a look at the events waited on, I'm seeing that the total time waited was 78 seconds simply on network traffic. So it is not an issue of the query or the SQL statement itself. The bottleneck here is indeed the network performance. What you also need to verify is the query that you expect to tune, is that shown at the top of the TKProf report. Also, does the query spend most of its time in the execute phase and the fetch phase, so not on the parse phase? And also make sure that the trace file contains data only from the recent test. Now the quiz is asking that in an environment with an application server that uses a connection pool, you use which tool to identify which trace files need to be combined to get an overall trace of the application. Is that trace session? Is that TKProf, Oracle SQL Developer, or the package DBMS application info? Well, the right answer is trace session, because that's the utility that you use to consolidate trace files into one consolidated trace file. So in this lesson, you have learned how to perform steps done before tracing, how to use application tracing tools, use SQL tracing facility and the end-to-end application tracing, and you should also have learned what is the meaning of the trace session utility, what is the purpose of the TKProf utility. The practice of this chapter covers the creation of a service, tracing your application by using services, and interpret the trace information by using the trace session utility and TKProf utility. Workshop number 3 of the SQL Tuning for Developers course. In this workshop, you will perform an initial setup and examine the indexed order by columns. This is the listing of all the scripts that are used within this workshop. To make your life easier, open all of these scripts beforehand in the order as they are specified in the guide. Those scripts can be found underneath the workshops folder. So here you can see that I've opened setup03, W03, W3 S1C script file and so forth already inside my SQL developer environment. So this workshop will show the possible usage of an index in the order by clause to tune a sort operation. You will perform several tasks to be able to use the indexed order by column. After all the tasks are done, you will verify if the index always produces a better plan cost. So what you will need to do first is, you will have to create a connection if you don't have one yet, called SH connection, allowing you to connect as the SH user to your database environment. Plus, you must also make sure that the user SH is granted the DBA role privilege, so that it has all the privileges that it needs during this workshop. So what you can do is you have the possibility of opening a worksheet as the sys user. And once you have done that, you issue the command grant DBA to SH. And you see that the grant has been succeeded. Then what you're going to do is you're going to run setup03.script file to set up the environment for this workshop. So in your SQL developer, you open setup03.sql, make sure that you connect as the SH user, and you're going to run this script. Now, what will this script do? It will actually create a table country in the schema of SH with country ID, country name, country subregion, and country region, with country ID being the primary key column. Then also a couple of records will be inserted into that country table. Also what's happening is that an index will be created upon the country region of that country table, and the optimizer statistics will be gathered upon that country table for all the indexed columns. Now, what you need to do is you now have to review the SQL statement inside ws03.sql. And if you open that script file, you see that I'm going to perform a select statement upon table country. And I'm going to look for those records where the country region equals Europe, and I'm going to order by country name. We know that country region is a column that has been indexed. And the script file, select statement, orders upon country name. Now what I ask you to do is to run w3s1c script file to execute the explain plan command for that particular select statement, and then show the execution plan of the last explained statement. So I'm going to go towards that file. Make sure that you choose here the SH connection, and you're going to execute the script. Now what do I see is when reviewing the execution plan for that select statement, that there is an index range scan upon the index upon the column country region. So for the where clause, he's going to use the index count country region IDX to locate all the entries with Europe, pick up the row ID, and via the row ID access the table to pick up all the records where the country region equals Europe. But an additional order by needs to be done because you're asking to order upon country name, which is a column that is not indexed. So an additional sort operation is needed. And you can see that the total cost of that select statement is 3. So the index upon the country region column is used, the cost is 3. That cost might differ depending on the settings of your practice environment. But then what we're going to do is, via this script file, we're going to create an index called count_cn_csr_idx, which is a concatenated index, a composite index on the combination of the column country name, country subregion. The order plays a very important role. So what we're going to do is, I have here this script file. In order to create this composite index on the columns country name, country subregion, choose the SH connection and run the script. And the index has been created. Once again, the order is country name, country subregion. Then I ask you to run this script file to execute the explain plan command for a select statement upon that country table, where we search upon country region, which is a column that is being indexed, and to order by country name, country subregion. That combination of columns has been indexed by that previously created composite index, and then show the execution plan. So what I'm going to do is I take that script file to do that explain plan command, sh connection, and then run the script. Now let's have a look at the execution plan. What do I see is that the index is being used upon the column country region to find all the records in my table country where the country region equals Europe. But what do I see is that the count CNCRS index, that it is not being used. Now, if it's not being used, as you see, it's not being mentioned inside the execution plan for that statement. If it's not being used, you can then add an index hint to allow to actually force the optimizer to use that concatenated index. So what you need to do is you take that script file w3s2b1. So that's this one. It's the explain plan command for the same select statement, but I'm using a hint to tell the optimizer to use that index. So we choose sh connection and we're going to execute that script. Now, what do I see is that at index, count CNCSR index, that composite index, that it's still not being used. So it is not being used, and I'm also still seeing that an additional order by operation is needed. Was the cost of that plan better than the one in task number 1? Well, I'm seeing that the cost is still exactly the same. This might differ depending on the settings of your practice environment. Now that index count CNCSR IDX, that composite index, is not used because one of those index columns in the order by clause should have the not null constraint. So what we can do is that if the index is not being used, if that composite index is not being used, take additional tasks to use the indexed order by column. So we're going to add upon our country name the not null constraint. This tells the optimizer that all the values found in the country name column are also all found inside that composite index. So via the script file w3s2c, I'm going to add that not null constraint to the column country name of my table country. So here I'm taking the script file, sh connection, and I'm going to add this not null constraint. And what we're going to do is we're going to repeat step number B to verify if now that composite index is being used. You can do this by using the script file w3s2d. So if you take that script file, you're executing the explain plan command for that same statement as you did before. sh connection. You're going to run this. And what do I see now is that the count CNCRS index, that it has been used. And you even see that the order by operation is no longer being done because it is using the index on the concatenation of country name and country sub-region columns. So it's already accessing the data sorted upon country name and country sub-region via that index. And you see that the cost is also lower because we do not have to do this additional sort operation. Now, what we're going to do now is we're going to drop that concatenated index and we're going to recreate a concatenated index, but now we're going to put the index order to first the country sub-region and then the country name. You do this via the script w3s3a. So I take this script file, I take the sh connection, and you see that the concatenated index, that the leading column is country subregion, and then we have country name. Before that, the order was different. So now I have a new concatenated index on the same columns, but with a different order in the definition of that index. And then what we're going to do is we're going to execute the explain plan command, where we're going to ask, okay, order by country name and country subregion. Now we do this by executing the script w3s3b.sql, which will also show me then the execution plan being used. So if I take that script file, I'm going to choose here the sh connection. I'm going to execute the script. And what do I see is that the composite index is being used. Now, if the index was not used, you can add an index hint to allow the optimizer to use that composite index and gather the execution plan. For this, you can use w3s3b1.script file, but in my case, it has chosen that composite index, and also the sort operation has been avoided. So in my case, there is no need to run the script file that includes a hint for that select statement. So the index is being used for that select statement. So you have performed several tasks to see the possible usage of an index in the order by clause to tune a sort operation. To end this workshop, you're going to launch the cleanup3.sql script file to clean out your environment for the next workshop. Choose sh connection and run the script. Now, when using the indexed order by column to avoid the sort operation, what should you consider? Well, all the order by columns should be in the composite index. That's true. The order by columns should be of the same order as those of the composite index. And at least one of the composite columns should have the not null constraint. So D, that all composite columns should not have the not null constraint, is not true. And the indexed order by column will avoid the sort operation, always produces better performance. This is also not true. This is not a certitude. Practices for lesson number 3, using the application tracing tools. In this practice, you're going to trace your application by using services, and you're going to interpret trace information by using utilities as the trace session utility and the tkprof utility. In this practice, you will trace a service. You will then interpret the generated trace files. You can find all needed script files for this practice underneath directory, Home Oracle Labs Solution application_tracing. Before you start executing the scripts, make sure that your environment has been set correctly. You open your terminal and you execute the command ./env and accept the default URCL. This makes sure that your environment variables have been set appropriately. Also, your environment has been initialized with the script file at_setup.sql before the class began. Content of that script file is listed below. Now, if you want to later on remake this exercise, you can reinitialize your environment by executing this script file yourself. How would you do that? Well, you're going to open a terminal. You're going to set your directory to application tracing folder. You connect to your database environment as the sys user, and you're going to launch that at_setup script file. Just to show you this, you see here that I've changed my directory to the application_tracing tracing directory. I connected as the sysdba user to my database instance, and I have launched that script file at_setup.sql that will drop user trace, recreate this user trace, give that user the appropriate roles and privileges, plus it's going to recreate 2 table spaces, and in that schema of user trace it's going to create a table sales, which is a copy of table sales of the sh schema. Plus it will also create a table sales2, which is a copy of the structure of table sales of the sh schema, but not copying over its data. Plus it's going to recreate a table sales3, which is simply copying over the structure of table sales of schema sh. You can launch the script file to reinitialize your practice environment to remake the exercises of lesson number 3. What you're then going to do is you're then going to execute 7 workload scripts that will be traced. All those workload scripts will run under the ORCL PDB service. It's that service that we're going to trace. Your goal is then to analyze those generated trace files to interpret what happens in those 7 cases. Now, what you will need to do first is you will have to run the shell script run_trace p0.sh, and after you have done that, you're going to enable the tracing for the ORCL PDB service. Let me show you this. So here I have another tab in my terminal, in fact. I've changed my directory pointing to the application_tracing directory, where you see shell scripts that bear the name run_trace p0, 1, 2, 3, 4, 5, 6, and 7. Well, first of all, you will have to run this particular shell script. And once that shell script has finished executing, you're going to log in into the database instance as the sys user. You have to make sure that the service ORCL PDB is active. That means that it pops up in the result returned by the select statement, select name from VDLR active services. And then you're going to use the procedure service module act trace enable of the package dbms monitor in order to enable the tracing of service ORCL PDB. You're interested in also capturing weight information. We are not interested in capturing information concerning bind variables. Once you have enabled then the tracing, you're going to run 7 shell scripts that will produce a workload inside service ORCL PDB, which is going to be traced. And with each shell script, trace files will be generated. So they're asking you to run the shell script run trace p1. They will ask you to run the shell script run trace p2. Then the shell script run trace p3, run trace p4, run trace p5, run trace p6, and the shell script run trace p7. Now I've already done that, so I've opened a new tab in my terminal. I did a listing of all the run trace files that end with .sh, and I'm launching the first shell script run trace p1.sh. This is going to produce a workload that is going to be traced for service ORCL PDB. Plus also what you get is that the trace files that this particular workload generates will hold the name mytrace_p1 and mytrace_s1. So the generated trace files that hold the name mytrace_p1 and mytrace_s1 are trace files that have been generated by tracing the workload that was generated by runtrace_p1.sh. Once that workload is finished, I'm going to run trace_p2.sh. The generated trace files will bear in their names mytrace_p2 as well as mytrace_s2. And it's the same story for running the workload runtrace_p3.sh. Once that is finished, I'm running runtrace_p4 workload. Then I'm going to launch runtrace_p5. If that workload is then finished, I'm running runtrace_p6. Now this runtrace_p6 workload can take quite some time. Now you can only go to the next workload to be executed if you see on your screen appearing, if you see here runtrace_p6 has finished, then you can launch the next and last workload runtrace_p7 as I have done over here. It's mentioned in the activity guide that if you look at runtrace_p6 script that you need to launch, it states clearly to wait until you see the message runtrace_p6 has finished before proceeding to the next step. Also, there is a note that this runtrace_p6 can take some time to execute completely. So wait for some time to finish execution and then continue. Now, once all my 7 workloads have been launched and for all workloads trace files have been generated, you're going to disable the tracing of the service ORCL PDB. So here you can see this, that I logged into my database instance as a sysdba user, and I've used the procedure service module action trace disable of the package dbms monitor to disable the tracing of the service ORCL PDB. Once you have done that, there is a shell script to show the listing of the generated trace files by the 7 shell scripts that you have launched before. So here you can see that if I'm launching the shell script show mytraces.sh, that there are a couple of trace files being generated. Now mytrace_p1, mytrace_s1 are trace files generated because of the tracing of runtrace_p1 workload. This is for the 2nd workload, the 3rd workload, the 4th workload, the 5th one, the 6th one, and the 7th workload. And then I will ask you in the activity guides to run the shell script merge traces.sh that will call upon the trace session utility to merge the content of the previously generated trace files into one file called mytrace.trc. So you see here, then I'm launching then this shell script merge_traces.sh, which will consolidate those trace files into one trace file that bears the name mytrace.trc. Then this consolidated trace file is not in a human readable format. No, for that we have the utility tkprof that we can let loose upon this consolidated trace file to generate a more human readable output file, and that output file will be called myreport.txt. So you see here in this tab in my terminal that I've launched the script file or the shell script tkprof_traces.sh, which is going to produce a file, myreport.txt, which is in a more human readable format than that consolidated trace file. Then they will also ask you, in addition, to run the tkprof utility over the trace file that was generated for workload case number 7 with the explain option set to your trace account. So here, in this tab of my terminal, I'm launching tkprof. I want that tkprof does its job on the file that ends with mytrace_p7.trace file to produce a more human readable output file called myreport_do.txt with the option explain. So all the commands in that trace file will be executed with the explain plan command, and the output of this is placed into myreport2.txt. So if I then would ask which file starts with myreport, I have myreport.txt, which is a human readable output file upon the consolidated trace file, while myreport2.txt is a human readable output file that has been produced upon the trace file that was generated by the 7th workload. You're now ready to interpret the trace generated for all different cases. You're going to interpret the consolidated and formatted trace file myreport.txt. Now the first case illustrates the consequences of using manually sized SQL area parameters such as the hash area size. The first statement in this case was executed by using a very small hash area size value. The immediate consequence was the number of temporary segments needed to execute that statement. So if I'm taking that workload, you see here that I connected as the user's trace. I've said that I'm going to control myself the area size parameters, and I have set the parameter hash area size to a rather low value. And then I have executed this select statement using the hint order use hash. If I'm looking at the trace file content that was generated for that particular execution of that select statement, what do I see is, so this is that select statement, and if I'm having a look, I'm seeing that there are quite some direct path reads and direct path writes upon temporary segments. Later on, that same statement was executed with the default SQL area parameters, which were sized automatically by the system to handle the needs. And if I'm then looking at the trace file content, I'm seeing that select statement again, which was now executed with automatically sized SQL area parameters. You see that in the wait events, I am no longer seeing direct write and direct read upon temporary segments. In case number 2, an almost identical statement was run 5,000 times, but each time a different literal was used to execute the query. This causes the system to parse almost the same statement 5,000 times, which is extremely inefficient, although the time precision is too low to give accurate information about the parse time of each statement. But the elapsed time and the CPU for the PL SQL block include the time that these 5,000 statements took to execute. So if I'm taking that shell script, you see here that I'm working with a loop with 5,000 iterations, and with each iteration of the loop, this select statement is going to be executed always using a literal value. So with the first iteration, I'm looking for object ID equal to 1. With the second iteration, I'm looking for object ID equal to 2. So it's almost always the same statement that I'm executing, but there's always a different literal value. And this is really inefficient for the parsing and the execution. If I'm taking this trace content, you see here, this is that PL SQL block with a loop with 5,000 iterations. And with each iteration, a select statement is going to take place with the where clause where object ID equals 1 and then 2 and then 3. And you can see here, this is the total CPU and elapsed time to execute those 5,000 statements. And what you will get is, you see here that I have a select statement, select object name from DBO objects, where the object ID equals 1. And what do I see is parsed one time, executed one time, and doing one fetch. And then if I go further into the trace file, I see select object name from DBO objects where object ID equals 2. I see one parse, one execution, one fetch. Then I see select object name from DBO objects where object ID equals 3. I see one parse, one execute, one fetch. And then I will see with object ID 4, 5, 6 and so forth. And at the very end I will see select object name from DBO objects where object ID equals 5,000. And what do I see is one parse, one execution and one fetch operation that is happening. So the system parsed almost the same statement 5,000 times. But then afterwards, when running this workload, I'm actually doing exactly the same select statement, but I'm making use of a bind variable. So what do I see is, I build up my select statement with a bind variable, and then I'm going to refer to that statement using that bind variable. I'm going to have a loop with 5,000 iterations that I have. And what you will have is that 5,000 times the same statement is going to be executed, but only parsed one time. So now if I'm taking a look at the trace content, I'm seeing here that PL SQL block where I'm executing 5,000 times that select statement using a bind variable. And what do I see is I have actually one parsing and one execution that is taking place. Now you will see here that I only see one time that select statement using that bind variable, and you see one time parsed but executed 5,000 times and it did 5,000 fetches, which shows that using bind variables will be in utilization much more efficient concerning the parsing time. In case number 3, we have captured tracing information for the SQL statement update sales set amount sold equal to 20,000. Now, what are the observations that we can see in the trace file and what can we conclude of this? Well, if I'm looking at the workload that has been generated, I'm doing an update upon table sales, setting the column amount sale to 20,000. But at that moment in time, there was no index yet available upon the columns product ID and customer ID. Now, what is the effect if I'm looking at the trace file? I'm actually seeing here this update. And what do I see is that in total, during the execution phase, only 2 records have been updated, but in total, 4,440 blocks were accessed to locate or to find records where product ID is 13 and customer ID is 987. And of those 4,440 blocks accessed, only 4 blocks have been accessed to perform the actual update. But this means that almost the entire table, and I can see that there has been a full table scan to locate the records that needed to be updated to an amount sold of 20,000. Then afterwards, I created an index upon the combination of the columns product ID and customer ID. And I did this update again. And I'm capturing tracing information. And what do I see is, I'm seeing my update statement. It's still updated to records, but you see that only 3 blocks have been accessed to find the records that need to be updated, and that in total 3 blocks were accessed to perform the update. And you see that via the index, he does not have to access all the blocks to find the records to update. Via the index, it can locate those blocks that contain the records where product ID is 13 and customer ID is 987. So this alternative case by having an index is much better because it uses an index to speed up the retrieval of the rows that need to be updated. We're going to interpret the trace generated for case number 4. The SQL statement executed contains the following string, sh.sales, where the amount sold is bigger than 0. If I'm looking at that workload, what do I see is that I have here my select statement that is being executed, and I see that I'm using a loop in order to perform the fetching. This is the very first time that I'm executing this. Now what do I see is when I'm looking at that trace file information, what do I see is that apparently this select statement performed, let's say, 919,000 fetches, and in total returned 919,000 records. That means that with every fetch, 1 record has been returned, which is quite inefficient. It means that the first execution of that statement, that it doesn't use the fetching mechanism appropriately. 1 fetch operation is done for every single row being retrieved. So then what I'm doing is I'm going to execute exactly the same select statement. But what I'm doing is I'm using bulk collect into. This means that I'm not going to do a fetch and return 1 record. No, I'm going to fetch multiple records with 1 fetch operation and return that in bulk to the application. And what do you see is if I'm taking the trace file information, in fact, this is that select statement, in fact, you see that in total it also returns 919,000 records, but it only needed to perform 92 fetch operations, which is much more efficient than 1 fetch operation that retrieves 1 single row. This technique is called the array fetch. We're going to interpret the trace that was generated for case number 5. And in this trace, we're going to look up the string using union all. We're going to interpret the trace generated for case 5. We're going to look up the tracing information by looking up the string union all. What are our observations and what are our conclusions? Now, first of all, some background information. As you can see, I'm performing an insert into a sales2 table, and I'm inserting the result of this select statement that performs a union all operation. I'm also performing an insert into sales3. I'm going to insert in that table the same result set as I've inserted into my sales2 table. So for both insert statements, it's in 2 different tables. It's the same amount of records that will be inserted. But what you need to know is that this sales2 table is actually being created in table space trace TBS. This is a table space that allocates extents with the size of 40 kilobytes, while table sales number 3 is created in table space trace TBS3 But in that table space, extents will be allocated having a size of 10 megabytes. So you have to imagine that if I'm going to insert a tremendous amount of data into table sales 2, a lot of extents of 40K need to be allocated. So this will induce a lot of recursive calls. While if I'm inserting into table sales 3, I'm inserting exactly the same amount of data. Yeah, but table sales 3 is created in a table space that allocates extents of 10 megabytes. So it means for table sales 3, less extents will have to be allocated because those extent sizes are 10 megabytes compared to the extent sizes of 40 kilobytes in that other table space. This means that you're going to have less recursive calls to allocate extents for table sales 3 than you have in sales 2. And this will be reflected in the timings for your execution phase. So what you will see is that to insert into sales 2, I see my execute timing, CPU time 3.7 seconds, elapsed time 4 seconds, while for inserting to table sales 3, I'm only having CPU time of 2.78 seconds and elapsed time of only 3 seconds. How do you interpret the trace for case number 6? Well, this case is much more difficult to understand. What you need to know is that when you launched workload number 6 to trace case number 6, the entire table sales has been locked completely by another transaction. If then this select statement is taking place upon that statement, the query needs to generate a lot of consistent read blocks to ensure read consistency. And it must do so for almost the entire table, causing a lot of undo blocks being accessed. Now, this is shown in the statistics by the large query value and almost no current blocks. So what I'm seeing here is my table sales is not 978,000 blocks big, but a lot of consistent read blocks have to be generated for that select statement to ensure read consistency. And that was due to the fact that there was an update first launched upon that table that is locking the entire table. That's why you're seeing a very large query value and almost no current blocks. For case number 7, which is also the final case of this practice, you should compare the content in myreport.txt with the content in myreport2.txt. So what do I have is, I have here my report.txt, where I'm seeing my select statements, and the optimizer decided, when I was executing that select statement, to choose for a full table scan. But then what I did is, I've actually asked the tk-prof utility, look for the SQL statement that was captured in the trace file for case number 7. Can you please run also the explain plan command for that particular statement? Meaning, if I would execute that statement right now, what would be that execution plan? And if I'm taking a look at my report.txt, I'm seeing that select statement. I see the execution plan that has been used when I executed that statement, when I was tracing it. But when I've asked tk-prof to run the explain plan command, he said, I think we would better off with an index. So in myreport2.txt, the row source section shows a full table scan, but the explain plan shows a table access by indexing. This is an indication that the explain plan might not be accurate.